So week 2, lecture 4, our final lecture this week is on standard scores. So standard scores, sometimes called z-scores, uh, whereas measures of central tendency and variability deal with whole distributions, z-scores, or standard scores, help us understand individual scores just by looking at the score. So any continuous variable, you can convert it to z-scores. And z-scores are cool. I mean, as cool as stat stuff gets, I guess. So uh, they're they're useful. How about that? In that they allow us to compare things that are really different, apples to oranges. So you can quickly look at z-scores of things from very different distributions, very different variables, and you can instantly know if someone's high or low and how high or how low just by looking at a single score relative to the rest of the distribution. So, who cares? I mean, fair enough. Um, Z-scores are useful, again, because you can interpret the meaning of an individual score from one number. So you don't need to know the mean and standard deviation, or neither does your reader, in order to know where a individual score falls in a distribution. So that's why maybe you care. So, for example, you could really easily interpret your grandma's rate your hotness score from, I think it was lecture 2, that survey. If she had given you the z-score, you wouldn't have to wonder about the shape and what was the central tendency and what was the variability. So they allow you to compare scores on different variables very quickly. But here's an important thing. Just because you take some variable and you convert it to z-scores, it doesn't change the shape of the distribution of that variable. So if it was normal from the get-go, you turn, intelligence scores, for example, you turn them to z-scores, it's still normal. If it was skewed, it's still skewed. It actually doesn't change the shape at all. However, if the scores are normally distributed and you convert them to z-scores, you can really easily do some interpretations, which we'll talk about, and that's what this whole lecture is. So the z-distribution, or the standard normal distribution, kind of looks like this. It is normal. It's got a mean of 0. It's bell-shaped. The mean, median, and mode are all the same, and at the middle it's 0. So I told you that in lecture 2 that in a normal distribution, the mean, median, and mode are all the same. In the z-distribution, the mean, median, and mode are all 0. The standard deviation in the z-distribution is 1. So the average score is 0. The average amount that scores differ from that mean of 0 is 1, up or down. So you can see one standard deviation above is positive 1. One standard deviation below is negative 1. The total area under the curve of the z-distribution is 100%. I mean, it's like that with every distribution, actually. But it's important to note that, which is a proportion of 1%. So 100%, or a proportion of 1. Because the median is the median, 50% of scores are below the median and 50% are above. Well, what's the median? 0. So 50% of scores in the z-distribution are less than 0, 50% are above 0. And here we get the fancy math part. Like, this is where z-scores actually have the most use, is that if you take the mean and you add 1 standard deviation to it and you subtract 1 standard deviation to it. So in that bottom graph, that's from -1 to +1. That's about 68% of all scores in the distribution will be the mean plus and minus 1 standard deviation. So that's, because it's symmetrical, it's 34% on the low side, 34% on the upper side. That is the 2 blue regions. And I'm rounding here just to make it easier. Like, technically, yeah, it's 34.13, but who really cares? So the mean plus and minus 2 standard deviations is going to give you the middle 95% of all scores in that distribution. So that is particularly useful. We use that for hypothesis testing. So 95% of all scores are within 2 standard deviations of the mean in the z distribution. And again, because it's symmetrical, that's about 47.5 on each side. So that is the -2 to the +2 in that graph on the right. And then finally, the mean plus and minus 3 standard deviations is the middle 99% of all scores in a Z distribution, and that is 49.5% on either side. So these are useful. We're going to talk more. These keep coming up actually during the course. So particularly the mean plus and minus 2 standard deviations, it's about the middle 95% of all scores in a distribution is going to be important. So this is the formula for Z's, and luckily we don't actually have to do these. SPSS is going to do these for us. So in this formula, X is a raw score on some sort of variable. X bar is what we call the X with the line above it. That is the mean of those raw scores. And S is standard deviation. So S is sometimes written as S, sometimes SD. In the Z-score formula, it's written as S. So that's the average amount scores differ from the mean. So if you pop a score in as X with the mean and standard deviation, you will get out a Z-score from this little formula. So standardized scores, that is Z-scores, they tell you, so the interpretation is how far a score is from the mean in standard deviation units. So is it, one standard deviation above the mean, one standard deviation below the mean, for example. And that's why it's called the standard deviation score. So Z-scores are used very frequently, and in this class we're going to use them to identify outliers. And actually we have already used Z-scores, and you just didn't know it. That skewness statistic is a Z-score. So when we look for skewness statistics that are bigger than absolute value of 2, we're looking for things that are in the very far out on the high or very far out on the bottom of the distribution. That is the lower 2.5% or highest 2.5%, which you don't really need to know. All you need to know is if it's bigger than 2, it's really far. So that's when we would say that a distribution is skewed with the skewness statistic. So scores that are 2 or more standard deviations above or below the mean, that is plus or minus 2 standard deviations, are outliers. So those are scores that are really far from the other scores in a distribution, just like when we get a skewness statistic that is 2 or bigger absolute value, we know we've definitely got something weird in our distribution. It's probably skewed, very extremely. So how do you interpret these Z-scores? You know that they're how far a score is from the mean in standard deviation units. Well, the sign tells you whether the score was above or below the mean. So above would be positive and below is negative. So if the Z-score is positive, that means the score, whatever the heck it is that you converted to Z-scores, is above the mean. If it's negative, it means that it was below the mean. If it's 0, which like never happens or rarely happens, means the score is exactly the mean. So, excuse me, that's what the sign tells you. The absolute value of it tells you how far. So if you ignore the sign and just look at the absolute value, bigger absolute value is further from the mean. The sign tells you if it's below or above. So the larger the value, the more different it is from the mean. And the interpretation is in standard deviation units. So for example, a Z-score of 2 is 2 standard deviations above the mean. So it's in that top 2% of values, because you recall that the mean plus and minus 2 standard deviations is 95% of all scores. So that leaves 5% that's not within that 95%. Half of it's below, half of it's at the extreme high. So that's 2.5 on each. A Z-score of -2 is 2 standard deviations below the mean. It's also equally far from the mean, but low, right? Because it's -2. So that is an extremely low score. They're both equidistant, though, from the mean, just in opposite directions. They're both equally far from the typical score in the distribution. First one is really high, and the second one's really low. So some example calculations. So typical IQ, I don't know if this stands for Binet or what, I don't remember which one I use, Wechsler. The mean is 100, standard deviation is 15. So if someone got an X score of 115, that is their IQ score was 115, if we do the little Z formula, we pop in 15 for the standard deviation and 100 for the mean, we get 1. We get a Z score of 1. What does that mean? Well, it means that that person's IQ was 1 standard deviation above the mean. Right? So it was higher than roughly 84% of all people. That is 50% below the median plus 34%. What if someone got a 108? So if someone got a raw score of 108, we popped in to the formula, we would get a z-score of 0.53. So it's positive, so they're still above the mean, right? Because the mean's 100 in the raw score distribution. It's about half a standard deviation above the mean. So what if someone got a IQ score of exactly 100? Well, you would get a z-score of 0. They got exactly the average. They have exactly average intelligence. 85, well, 85 is, if you pop it in the formula, it's -1 z-score. They're 1 standard deviation below the mean. So equidistant from a 115, just below the mean instead of above the mean. So you can also go the other way. You can get a raw score from a z-score, and I ask you one of these on the problem this week. So here's the formula. To get an x from a z-score, you take their z-score, you multiply it by the standard deviation, that's z times x, and then you add the mean to it of the raw score distribution. So there is one of those coming up. So for example, if someone's z-score was -0.8, so 0.8 standard deviations below the mean. And we knew the mean was 100, standard deviation was 15. We pop in that little formula. Their score was 88. Their raw IQ score was 88, which corresponds to a z-score of -0.8. So when you pop these into SPSS, remember to follow the order of operations. That is, it's been a while since a lot of us have done math. So there was this order that things are done in, starting with parentheses, then exponents, then multiplication or division, and finally addition or subtraction. So it makes a difference when you fill the formula in the SPSS. You have to make sure it does things in the order you want. And so basically, you have to put something in parens on your homework, which I think is pretty clear now. All right, so there are other types of standard scores that are more frequently used. Like, well, actually, z-scores are the most frequently used, but t-scores are the most frequently used for actual evaluation measures that like clinical psychologists and school psychologists administer. They're called t-scores. So basically, people don't like negative numbers, so they shift everything up so that there's no negative numbers anymore, and those are called t-scores. So they're often used to compare someone's performance on a standardized measure, like an IQ test, to the score that's typical for their age and sex, for example, in the back of a test manual. T-scores are frequently come out if you take a tests and measures class. So they have a distribution, usually anyway, of 50 and a standard deviation of 10. So they've shifted everything up by 50, right? Instead of a mean of 0, it's a mean of 50. Instead of a standard deviation of 1, it's a standard deviation of 10. So to transform z-scores into t-scores, which you do on the homework, here's a little formula for doing that. To get a t, you start in the parens, you take their z-score and you multiply it by 10, right? And then you add 50 to it. That is the mean. So if you do that, you'll convert a z-score to a t-score, which you have to do on the homework. So let's say you had a z of -1. You want to convert that to a t-score. We're going to pop it in where the formula on the line above says z-score. And you get that they had a raw score of 40 on the t-scale. Or excuse me, so they had a t-score of 40 is the equivalent of a -1 z-score. So again, that's still 1 standard deviation below the mean. So instead of -1, it's 40. So you have to know that t has a mean of 50 and a standard deviation of 10. So 50 minus 10 is 40. That's 1 standard deviation below the mean. This is sort of why z-scores are more intuitive once you get used to negatives. because you just know negative 1's one standard deviation below the mean. Whereas in t, you'd have to know what 40 meant. So finally, let's try some of these before I set you loose to go do them on the homework. So assume that you have a perfectly normally distributed variable. What percent of scores are more than one standard deviation below the mean? And so you have to be careful about, like, there's underlined words here. I'm trying to make a point. So below the mean, more than one standard deviation below the mean. So you want to know what percent of scores are below -1, right? So one way to get that is to do, well, we know that the mean is 0 and 50% of scores are below that. We know that about 34% are between 0 and -1. So 50 minus 34 gives you 16% of scores are in that orange, yellow, and green area. If you summed them up, roughly. So this is different. Notice that the word underlined is from the mean. What percent of scores are more than one standard deviation from the mean? Well, from is not below or above. From is either direction. What percent are one standard deviation from the mean? So that's going to be the orange, yellow, and blue on both sides of this distribution, right? So the easiest way to answer it is, say, 16 plus 16. So the answer we got in the last one gives you 32%. 32% of scores are either one standard deviation below the mean or one standard deviation above the mean, which is one standard deviation from the mean. So let's say, though, instead of a normal distribution, you've got something that's positively skewed. So what percent of scores, if you converted this to z's, are going to be above the mean? So it's tricky because we don't know. So we know that the mean gets pulled towards the tail, so it's going to be something maybe less than 50. That's about all we know, because that mean gets yanked up towards the tail, so the mean is closer to the center. Excuse me, the median is closer to the center, and the median is always the median. It's always got 50% of scores below it, 50% above it, whether it's skewed or not. So the important thing I wanted to point I wanted to make here is that just because you convert some distribution to z-scores doesn't magically make it normal. So a skewed distribution is just a skewed bunch of z-scores. So finally, what percent of scores fall above the median in this distribution that's positively skewed? Well, the median is the median. It's going to be 50% of scores are going to fall above the median in any distribution, really.